You can check. I have shared the screen.
Yes, sir.
Screen is visible to you.
Yes, sir, it is visible, sir.
Okay, so center of mass, we discussed about the center of mass of some bodies like a rod is there. So what is the process? The process is very simple. So for continuous mass distribution, if the mass is distributed continuously, like there is a rod, suppose, okay. So in such situation, one, for example, like this here. So first of all, you will choose one element and then you will use the formula of the coordinates of the center of mass. So for example, you already know that x coordinate of center of mass is given by integration x dm. Okay, so instead of m1 x1 summation, you are doing integration x dm divided by, again, in place of m1 m2 m2 total mass, you are doing integration of dm, or you can simply write total mass. Within proper limit, you will do the integration from x1 to x2, here also from x1 to x2. That x1 x2 will be already clear from the question, depends on the situation. Okay, so in this you have any doubt?
No,
Now here, what is dm? So dm is the mass of the element. So first of all, you can choose the element, and now if you have to write, so here in case of a rod, I'm choosing an element of length dx. So then mass per unit length of the rod multiply with dx. This will be the mass of the element. Where is the element located? Means what is the x coordinate of the element? That is this here, x is given. Okay, so this is x, which is variable here, that you will vary from x equal to 0 to x equal to l, like in this situation. Okay, this is clear. When you will substitute this integrate within proper limit, you will get the answer. This I think we already discussed in the last class. In this you have any doubt, you can ask. You are not audible. You have any doubt? You can ask your doubt.
sir. And, sir, no doubt I understood.
Okay, so then let's go to the next. Now suppose you have to find center of mass of a semicircular ring. So actually, based on the shape of the object, your choice of the element will change. So for example, here you can see that this is a circular ring. So it is better to take a part of this circular arc, you know, a small part of this circle, which will be an arc. And suppose this a small arc is subtending an angle d theta here. Now again, the concept will be same. Here, one thing you have to understand, that center of mass will always lie on the line of symmetry. For example, here, if you look at the x-axis and you look at the y-axis, x-axis is not the line of symmetry, because above x-axis and below axis, the symmetry. Here you can see on both sides of y-axis, the mass distribution is exactly identical, right? So here center of mass will have only the y coordinate here. Okay, so a center of mass will definitely lie somewhere on the y-axis. On x-axis, center of mass, because the mass distribution is identical, so x coordinate will be 0. Okay, so because it lies on the y-axis, now you need to only find the y coordinate of the center of mass. So y coordinate of COM, so use the formula first of all for the continuous mass distance. So y dm upon summation of total mass, right? Integration dm. And now within proper limit. Okay. So when you will express dm, how you will express dm here? So here also you can write dm is equal to lambda into its length. But what is lambda here? Lambda into its length, let's say length is dl. But what is lambda here? So first of all, lambda will be given to you in the question. If suppose lambda is not given, charge on the ring is given, then you can do charge by length. So then you can do charge by total length of the ring. Because it is a half ring, so total length will be pi r. This is lambda, total length, charge by total length into dl. What is dl? dl is length of the element. What is element? Element is a small arc. What is the length of the arc? The r d theta. Understood? This is how you will find dm. Then you will substitute this dm in this equation. And you can see dm is a function of here. It not dm, like y. You can say y is a function of, will come as a function of theta. And so everything ultimately you will get y dm as a function of theta. Okay, and then theta you can vary the limit from 0 to 180 degrees. This angle here, minimum it will be 0 and maximum it can increase, go up to, this means 180 pi, 0 to pi you will integrate after that. What is y here? Y is the y coordinate of the element, which you can write as r sine theta, right? In this triangle you can see clearly r is the radius, this is r is the radius. This angle here is the theta. So this will be r sine theta. Is it clear? After that, integration is there. You just need to integrate. You'll get it. You have any doubt, you can ask here.
No.
No doubt. So like this, Anna, have you tried this derivation?
Right.
Similarly, here center of mass of a hollow sphere is there. Okay. So now you just try, because the process is same all the time. You have to do the same thing. You have to repeat it again and again. Here again, you can see that the center of mass will lie on y-axis somewhere. So ultimately, you should know the derivation, but then ultimately you will have to remember the center of mass coordinates for all the bodies. Because in questions, they will not ask you to derive the center of mass. Mostly you will have to remember it, but derivation is also important because they can design some question where derivation will be there. Here you can see in case of a spherical cell, on the surface they have taken a strip of width r d theta on the surface. Strip of width r d theta on the surface. This width is r d theta, r d theta. So it is like you can imagine like a strip on the surface of the sphere whose radius is r cos theta here and width of that strip is r d theta. Here how you will find dm, because here mass is not distributed on length only, on the area, and because element is a small area of the hemispherical cell. So here dm you will not write lambda into, here you will write sigma, surface density or areal density into area of the element. Okay. And what is sigma? Sigma is nothing but total mass by total area. Here you can see total mass by total area. Area will be curved surface area. Curved surface area of the complete sphere is 4 pi r square, but it is a hemisphere, so m by 2 pi r square. And after that, area will be simply its circumference into width. This strip is there, and its circumference is 2 pi r and its width is r d theta. So if you will cut and open it, it will simply become a rectangle of length 2 pi r cos theta and width r d theta. So its area will be simply length into breadth, which is 2 pi r cos theta, which is its length. Its width is r d theta. Tell me, here you have any doubt? You can ask here.
No, sir.
Your voice is not audible.
What doubt, sir?
Okay. Okay, so I'm skipping this because ultimately you have to go through the derivation in your book, Narayana book, it will be given. Only integration is there for follow the process. Ultimately, remember all the go through all the derivation and remember all the values. So now I am skipping all this. Ultimately, you have to remember this. For rod, it is here. For ring, it is here. So for different body, the center of mass, final result that you have to remember, and you also should know the derivation. Now the next is motion of center of mass. Okay. So if center of mass is moving, then you will have to find the velocity of center of mass. Now you clearly know the formula of position vector of the center of mass. Okay. So from the formula of velocity, we already know that velocity is nothing but dr by dt. So here you have to find velocity of center of mass. That will be also rate of change of position vector of the center of mass. So just write the formula of position vector of the center of mass and differentiate it. Differentiating it both sides, you will get the formula of velocity of center of mass. You already know the formula of position vector of center of mass. Now if you will differentiate it, you will get the formula of the velocity of center of mass. So velocity of center of mass vector form will be, so because it is m1 r1 plus m2 r2, and now you will differentiate. M1 is constant, dr1 by dt, that will become v1. So then it will become m1 v1 vector plus m2 v2 vector, like that, upon total mass. Total mass is constant, so directly I am taking upon total mass as outside. So upon total mass, this is constant. Constant I am taking outside. And then the first term is m1 r1 vector. Its differentiation will become m1 v1. Second term differentiation m2 v2. So now directly I am writing summation mi vi vector, where vi is the velocity vector of individual particles. I will vary from 1 to whatever is the total number. Let's say n is the total. Understood this? I have not done anything. I have just differentiated both sides. Tell me,
Yes, sir. Understood, sir.
are you getting it?
Think, sir.
Yeah, so here V1, V2, V3, V4 are all the velocity vector of the individual particle with respect to the origin. Now again, exactly same result for the acceleration. For acceleration, what you will do? Again, the velocity expression you will differentiate. So when you will differentiate velocity equation, you will get the acceleration equation. Acceleration of COM. So acceleration of center of mass will be again dv by dt of center of mass. Then you will get summation. Total mass is already outside because it is not going to change. It is constant. And then, so summation mi, vi was there, mi is also constant. Means for individual particle, for each separate term you will differentiate. No? So first term you will differentiate, you will get m1a1. Second term you will get m2a2, like that. So miai will come. All the formula are identical. You can see here. In all the formula in denominator there is total mass. Velocity formula mi summation mi vi Acceleration formula summation MI AI. Position vector formula summation MI RI. Are you getting? Just by differentiating both sides, you'd get this expression, right? So you got the formula of acceleration of the center of mass also. Now, now here you can see external force on the system. Now here you have to understand that suppose there are n particles in a system, and just now you have seen that ACM is equal to M summation mi ai upon m. Now from here, can I write that total mass of the system, if I cross multiply, total mass of the system multiplied with acceleration of the center of mass. Now see, this is the second law is coming now. For body, I told you now, is equal to summation MI AI, right? Now, if you look carefully, what is MI AI? MI is, है ना? That will be mass of ith particle, acceleration of ith particle. So all these are particles, right? So if I look at any one particle, so for particle we already know the Newton's law. On a particle, its mass into acceleration will be the external force acting on it. So if you do that, m1a1 will be nothing but f1 force on first particle, m2a2 will be nothing but force on second particle, m3a3 will be nothing but force external force on fourth particle, so on. If you go on adding all, what you will get is the net force, total force on all the particle. When you add total force on all the particle, add vectorially, that is nothing but net external force on the system, right? So now from here you can clearly see that, okay, total external force on the system, which is this, is coming out to be equal to mass of the whole system into acceleration of the whole system. So now this is the Newton's second law for a system of particle, for a body.
First law we discussed second law for a particles only, no, so a particle.
Yes.
Yes.
So second law for individual particles, you know, so M1A1 will be equal to F1, force on particle 1. Similarly, M2A2 will be the force on particle 2. But now here you can see it is summation of all the force. So it becomes total external force on the system. And that is equal to total mass. And most importantly, this is acceleration of the center of mass and not individual particle. Are you getting? So now this expression is not for individual particle. This expression is for the whole system. This is the Newton's second law equation for the whole system, which looks exactly identical to the Newton's second law for particle. But there is a major difference. The difference is that now you can write the net external force as mass of the system into acceleration of the center of mass. So different particle can have different accelerations, but net external force will be always equal to total mass of the system multiplied with acceleration of center of mass. In this you have any confusion, you can ask.
There no doubts.
Okay, so now from here you understood that net external force is equal to mass, total mass of the system into acceleration of the center of mass. From here you should understand that this is net external force on the system is equal to mass into acceleration. From here you should understand that center of mass of a system will accelerate only if there is an external force, net external force acting on the system. If net external force acting on the system is zero, center of mass of the system cannot accelerate, but individual particles can accelerate. Even if net external force on a system is zero, individual particles of the system can accelerate. But acceleration of center of mass will only depend on the net external force on the system. Center of mass cannot accelerate without external force, net external force. But individual particles can accelerate even if the net external force on the whole system is zero. Are you getting it?
If the individual particles, if they move with the constant velocities also, uh, but the at center of mass cannot move with instant.
No, yeah, that is also possible.
That is the only case where external force will be zero. No, sir. If there
No, no, no.
there is no other case,
Cent individual particle can accelerate. I'm not saying uniform velocity, can accelerate, but center of mass cannot accelerate.
yes, sir.
That is also possible.
Yes, sir.
Okay, so let's go to the. Now, this is very important for many questions you will see. Displacement of center of mass of a system of particle. Displacement of center of mass also you can write in a different way that if suppose center of mass is there and it is moving, so then what is displacement of center of mass? Displacement is nothing but change in position vector, which is nothing but v into, displacement will be nothing but integration. I can write vcom into dt. Maybe vcom is constant or maybe variable. So in any small time, if I have to find the difference, the displacement of com, I will use this formula from 0 to whatever is the time it is. I have to find the displacement. I will integrate, I'll get this. Okay. Or if you assume that it is if you assume that you are finding the displacement in a very small interval of time, then let's say you can write it that it is dr, and that is equal to integration only vdt, no integration, vcum dt. And then if you write the formula, then it will become summation mi into vidt. And now here you can see that this, and don't forget this vector sign, this vidt will nothing but individual displacements. So vidt is displacement of first particle, v1 dt, v2 dt is for second particle, v3 dt is for third particle. So ultimately you are getting that, okay, displacement dr or maybe delta r will be given by this. And we forgot one more thing here, because in formula of VCOM it is this divided by total mass. So divided by total mass. In this you have any doubt? So now you will remember this formula for the calculation of displacement of center of mass, but you know that it is calculated by this method. Is it clear?
It is clear, sir.
Okay. Okay, so now from here, already know now what is linear momentum of a system. Linear momentum of system will be total mass of the system into velocity of the center of mass of the system. And again, now you can apply the Newton's second law, and then you will get here. You can see this is total linear momentum of the system. Again, you differentiate it both sides. So from here also you will get the same equation which you already derived for Newton's second law for a system. And you will understand that if net external force on a system is zero, then linear momentum of the system will remain conserved. So if now here you have to understand, right now we are not talking about individual particle, we are talking about system of particles. So if net external force on a system, it's not about individual forces, net external forces on a system, so that is nothing but sum of all the individual forces acting on all the particles. So that is equal to you know dp by dt. And now here you have to understand that when I'm writing dp by dt, what is p? P is also the linear momentum of the center of mass. Okay. Or you can say linear momentum of the body, because linear momentum of body is nothing but we say that okay, total mass is concentrated at center of mass, so linear momentum center of mass. So you can also say total mass of the linear momentum of the system. Now from here it is clear that if net external force on the system will become zero, then the momentum will become constant. That is nothing but law of conservation of linear moment. That if net external force, by default it is always the net force, becomes zero, then linear momentum of the system cannot change. Linear momentum of the system cannot change, so it will be constant. Means m into vcum will be constant, means vcum will be constant, right? So exactly same thing here also. Now again you can apply the law of conservation of momentum to gun and recoil during firing a bullet. Okay, this type of question you have already done, assuming the bullet as a particle, gun as another particle. You have done it already. Okay, so we are done with the center of mass related things. We can go to some questions from that. So let's try some questions from center of mass part. For example, this is the question. Suppose in this question you can see that the x and y coordinate of the center of mass of a uniform L-shaped lamina of mass 3 kg is L-shaped lamina. So I think there is some problem in the diagram. It's not okay. I think I got it. It is somewhat like this. The diagram, some part is missing in the diagram, I think. It is like this. This is the complete shape, L shape. From here, this complete L. Can you see this? Complete L shape? Yes, now this is complete. Now here, if this is a L-shaped lamina, regular lamina, unless and until it is mentioned that it is non-uniform, you will always assume that okay, it is uniform, unless it is mentioned. Now, if it is uniform, what we can do is we can simply break it into two parts. So one part I can break it like this, and the another part, so I'm taking this as one part, yellow color, this as one part, and this part as another part. Can you see this?
Yes, I can see.
Yeah. Now you can treat both the part as separate body, and you have to find center of mass. Now, because they are regular body, so their center of mass will be at their center. So now I can replace the complete first body with a point where its entire mass is situated. And the same I can do for second body. Again, I can replace the second part by a point mass where its whole mass is distributed. Now here you have to understand that complete mass of the lamina is 3 kg. Complete mass of the lamina is 3 kg. But because the mass is uniformly distributed, so we can say that its mass will be proportional to its area. So if you see the area of this part, first part, is 2 into 1. So it is 2 meter square. This part is 2 meter square area. Whereas this part, it is 1 meter square area. What does it mean? That part will have mass 2 kg. This part will have mass 1 kg. Because the area is half, so mass also half. Mass is distributed in area uniformly. Now treating these two parts as simply two particles. Now your question is just reduce to two particles and find their center of mass coordinate. That's it. Now to find x coordinate, you can use the formula that x coordinate of center of mass will be summation m1, है ना? So now mixi. So now mass of first particle, which is 2 kg, into its x coordinate. Yeah, tell me. Tell me, you have any doubt? You can ask.
Thoughts.
Okay, so just use this formula and you can calculate. Total mass is 3 kg. Simplify, you'll get the answer. So I think you are getting x coordinate as 5 by 6 and maybe y coordinate also 5 by 6. You can check it. Okay, understood. You have any doubt in this?
No doubt, sir.
Can we go to next?
Yes, sir, we can go, sir.
Okay, so let's go to the next then. Okay, so I think they have not given much question on center of mass. If you want, you can try this. Have you already done this type of question? Then you can just leave it. See this. If you can do this quickly, then we'll go to the next. Try this question. Give me 1 minute. Got it? You can ask your doubt. Can you do it?
Form directly we can get first.
Sorry.
By directly applying formula we can get first.
Hmm. Yes. Okay. So let's try some other part now. Okay. So basically, we are studying center of mass to understand the rotational motion, and also, like many questions you can solve in center of by understanding center of mass. So it is not directly about the center of mass. Most of the time the questions are where center of mass is also involved. Okay, so now we will move forward and we will go to the rotational motion part. We'll start the rotational motion. So first of all, let's start with the definition of the rotational motion. What exactly is the rotational motion? Okay. So first of all, till now we were studying the translational motion, okay, where a particle start from one point and goes to another point. But now we have to study motion of rigid body. Earlier there was particle. Everything we are treating as particle. Particles can only do translational motion. Particles cannot do rotational motion because rotational motion is not defined for a particle. Rotational motion is only defined for rigid bodies. Only bodies rotate. Now, a rigid body can also do translational motion and can do rotational motion and can do rotation plus translation both. So, first of all, let's only try to understand about the translational motion. Now, here you can see the first case. Case 1 you can see. Now, if you look at case 1, when the rod is rotating, look at the body. Look at the body. This is the body. Forget rod, only focus on the body. So when the rod is rotating, Is the body rotating or body is just translating? Translational motion means body going from one position to another position without any change in orientation, without rotation. Body going from one point to another point in such a way that all the particles of the body have same displacement, same velocity, same type of path covered by all the followed by all the particles. So here you can see that if one particle is going from here to here, the second particle of the body is also doing exactly same displacement in the same time and following exactly same path. If one is going in a straight line, another will also go in a straight line. Are you getting? Look that there is a straight line drawn on the body. If you see clearly, you will find here a straight line drawn on the body. See this line. And look, when the rod is rotating, focus on this rod. So when the rod is rotating, body is connected to it, but body is not rotating. Look at the line. The line is always horizontal. In all the three cases, if you focus, the body is not changing its orientation. The entire body is just moving in a from one position to another position without changing its orientation. So the first case is representing pure translational motion. In pure translational motion, all the particles of the body have equal velocity and acceleration at all the instant. I'm not saying at all the instant velocity will be same, but at any instant, velocity of all particle will be same. Maybe next instant velocity of all particle different from what it was at time t1. At time t2, maybe velocity is different. But then at any instant, velocity of all particle of the body at any instant will be always same. So at t1 time, if you see, the velocity of all particles will have some value, same value. And again, if you see at time t2, then all particle will again have a same velocity. Maybe the velocity at t1 time and t2 time is different, but all particles at every instant will have same velocity. And they will cover equal distance and displacement in equal time. But now focus on the second diagram. Now you can see that the body is rotating. Now the body is not just translating. Look at a straight line drawn on the body. It has changed its orientation. Can you see this? So here now you will say that yes, now this body is rotating. Now how will you describe rotation? So a body is said to be in rotation if all the particles of the body goes in a circle. So here you can see the particles of the body will be going like this in a circle, and center of all those circles lie on a line which we call as axis of rotation. But now here you have to understand that this we are talking about pure rotation. Pure rotation. Only rotation means pure rotation. For example, earth motion is not pure rotation, because earth is rotating as well as it is also revolving around the sun in a circle. So if you say earth motion about its own axis, then it is pure rotation. But complete motion of earth is rotation plus that translation, where the entire earth is going from. So if you have to focus on understand what is pure rotation, focus on the ceiling fan. A ceiling fan is in pure rotational motion. Whenever a body moves in such a way that all the particles of the body goes in a circle, goes in circles of different radii, and center of all those circle lie on a line which we call as axis of rotation. then we say that the body is in pure rotation. Now, in rotational motion, each particle of the body, it is different particle of the body can have different velocity at the same time, and different particle will also cover can also cover different displacement and different distance in the same time. But that is not true in translational motion. Now tell me, have you understood or you have any doubt you can ask? You are not audible. Yes, you are not audible. You understood? You have some doubt? You are not audible.
Understood, sir.
Okay, then why you are not replying in the first time? Why after 10 times you say not understand or understand? Okay, so now here you can see motion of a rigid body. Now in the first case we are talking about pure rotational motion, and it is the rotational motion about a fixed axis. For example, your ceiling fan. My voice is clearly audible to you or not? Not audible?
You are clearly audible, sir.
Okay. Okay. So rotation about fixed axis. So whenever a body rotates about the fixed axis, okay, we say that it is pure rotational motion, and here all the particles of the body will move in a circular path, and center of all those circle lie on the axis of rotation. Here also you have to understand that axis of rotation will be always perpendicular to the plane of rotation, will be always perpendicular to the plane of rotation. So if plane of rotation is xy, plane of rotation means all the particles moves in a circle. So if all the particles are moving in xy plane, okay, we will say that the plane of rotation is xy plane, and we'll say that the plane of rotation is xy plane, and then axis will be perpendicular to the plane of rotation, means axis will be along z axis in that case. Okay, axis of rotation is just an imaginary line. It is not that actually there is some line passing through the body. It is just an imaginary where we assume that all the center of all the circles will lie on that particular line actually. Okay, so if you draw the locus of all, say the center of all the particle, if you just join them, then you will get an imaginary line which is axis of rotation. So motion of a rigid body. So already we discussed pure rotational motion. Okay. And now to understand more about the rotational motion, first we will introduce some of the angular variables. Okay, so these are very important to understand these angular variable. The first one is angular displacement. Okay, so just like there is pure simple linear displacement. Similarly, there is angular displacement. Just give me 1 minute. So just like you studied displacement and acceleration, velocity, similarly, all those variables were used to describe the linear displacement, linear motion. Similarly, to describe angular motion, we introduce some angular variable. For example, angular displacement. Now, angular displacement is simply, okay, you can see that the if there is a body and on the body you just draw, you, in simple way, you can simply say that the angular displacement is simply the angle rotated by the body. Or you can say that suppose if there is a fan and fan rotates by pi by 2 radian, then all the particles of the fan also rotates by pi by 2 radian. So you can also say that the angular displacement, you know, is simply the angle rotated by a particle of the body. Angular displacement of particle is same as the angular displacement of the body. Now what is angular displacement of the particle? So because the particle is going in a circle, if suppose at any particular time this is the particle and this is the position vector of the particle. So in any t time, if position vector of the particle rotates by theta angle, okay, then theta is the angular displacement of the particle and of the body. Now when a body is rotating, for example, a